So, and this is typically what I would recommend for this kind of tutorial. So on the left, you see my terminal. I have two windows open. So the first one I will use to log onto the cluster, and the second one is where I will store files for local, either post-processing or if you just want to save them after the session. And on the right, I have my browser window open. One is, of course, the tutorial. So that's here the landing page of the tutorial itself. And the other, as we will see in a second, is our graphical interface for FHI-aims, which is called GIMS. And that's used in parts of the tutorial as well. Okay, good. That all worked. So what we then need to do is log onto the cluster. And I will briefly show it to you. I think some of you are already logged in. But the idea is the following. You SSH in your terminal with your username. So in my case, it's Lion at the IP address that was sent to you. It's the same for everyone. Then you use the password you have been sent to log onto the cluster. So this should give you this message. It might be that you first have to accept the SSH confirmation. So just type yes, and then you are logged in. And in here, you already have a few files that have been prepared for you. So the first two are folders and reference results that we'll look at later. But there's a README, which is quite important. And this README just summarizes essentially what kind of files we are, what kind of system we have. So this is a system with compute nodes where each node has 64 cores. And everything you need for the tutorial comes pre-installed. So we have already set up the FHI-aims binary, all the Python packages, and whatever you would need to run this tutorial in advance, so you really don't have to do any setup. What we're using is a Slurm, is the submission system. So you will submit jobs onto a queue. And importantly, if you want to copy files back to your local machine, you can use the rsync comment, for example, this one here. So you just replace the username with your username as well as the IP address of this cluster. And this will then download the files. If you don't want to lose the files or look at them at a later date, you can do so by this. And yeah, we have also prepared a submission script. So this you don't have to touch at all. This is what we'll use throughout the tutorial to submit calculations. So it's a simple one node calculation with some time limit. But as you will see, most of the calculations are quite quick. Okay, so that's it for the introduction and how to get on the cluster. Is there anyone having issues at this point? So is anyone here not able to log onto the cluster? Or is there a question in general before we begin? Yes, thank you. I see C1 in the chat. That's all good. Great. Yeah, I think we see also at least 5 here logged onto the cluster, so that's good. If there are more people struggling or want to get logged on, just let us know. We can help you, of course. So yeah, let's start with the basic intro of the tutorial. So yesterday in the webinar from especially Ray Miyazaki, you heard one of the use cases of FHI-aims on how to calculate DFT properties for heterogeneous catalysis. And that was one of the main motivations also to do this kind of tutorial here, to exemplify for you how can you actually run these kinds of calculations, what do you have to, or what are the pitfalls, what do you have to remember, how do you set up these kinds of calculations. So the case study that we'll look at is actually calculating adsorption energies, and specifically CO2 adsorption energies on a catalyst system, which is a cobalt cluster supported by an amorphous silica slab. So if you remember the talk yesterday, that is exactly the same system that was covered by Ray Miyazaki. There's a first part, which is a bit more general. So the preparations here, which I will just briefly go through. As I mentioned, you don't have to do the setup here. It's already done for you. FHI-aims is installed as well as CLIMS. So if you're unfamiliar with CLIMS, it's our command line interface written specifically for FHI-aims. This simplifies the generation of input files. It also can do some other cool stuff, but in our case, we will use it mostly for the creation and of input files in our case. Again, all this is pre-installed, but if you want to do this stuff locally, you would, of course, have to follow these preparations. And then, let's start with the very general introduction. So before we go to the very complex catalytic system, it might be that some of you are not familiar at all with slab calculations. So we wanted to give a very brief intro on how to do these kinds of calculations. So in general, what is a slab model? Well, you use a slab model to simulate surface properties. So you have your slab here inside the cell, and you add vacuum inside the cell as well to remove the interactions between neighboring slabs. So neighboring in this sense is, of course, we have periodic boundary conditions. So in that direction, there should be minimal interaction between images of these slab models. And what we want to learn here is, one, how can we create such a slab with our GUI GIMPs? And then the other, how do we submit a simple slab calculation for this specific example? And here we're looking at a very simple silicon 100 surface. As I mentioned, these are really the basic concepts. So we didn't want to overcomplicate this part. If you're interested in more advanced functionality, that means, for example, how do we calculate work functions, surface energies, electrostatic potential outputs, all these kinds of things. They are described in two separate tutorials, which you can, of course, also look at, which is a slab calculation and surface simulation tutorial in itself. And then we also have an introduction to ab initio thermodynamics, as well as the replica exchange grand canonical approach. So those tutorials are also available. Feel free to check them out if you are interested in these kinds of calculations. So then I think we can start. And all this work here I will do on the cluster. So that's here why I'm on my left tab of the terminal. I start creating a working folder. So silicon surface here is a working folder. And what we want to look at is the silicon bulk. So I will create a folder for the silicon bulk and then just copy in this geometry file. So within FHI-aims, you really only have two mandatory input files. That's a geometry file and a control.in file. So a geometry.in file, as the name implies, just contains the geometry. So in this case, we have the conventional unit cell for silicon. So that's a diamond cubic structure with a lattice vector of 5.43 angstrom. And you see here also the fractional atomic positions for the 8 silicon atoms in this conventional cell. And this file you can just save. We will use this structure as the starting point to construct our slab model. So, and as I mentioned here, it's also mentioned in this note briefly, this has already been relaxed and then essentially just refined to remove the numerical noise. It already uses light species defaults as well as the LDA functional, the same that we will use for the slab later on. So what we want to use now is GIMPs. So GIMPs, as I mentioned, is our GUI. So feel free to open a new browser window with this link. And this should bring you here to the GIMPs interface. Now, GIMPs can do several things for you. For FHI-aims specifically, we have several calculation apps. What these calculation apps mean and represent are ways on how to create input files. So, for example, control.in files for specific workflows. So if you're just interested in a band structure, maybe you want to run a GW excited states calculation or a molecular dynamics calculation, or just a very simple total energy relaxation one. And this can help you simplify these steps. But what we're interested in or focusing on in this part of the tutorial is actually the structure builder. So here you can manipulate geometries. So let's open the structure builder now. This by default opens a preloaded structure, but we are of course now more interested in the silicon bulk. And now you have two options. The first option, which I just briefly do here, I will not type in everything for one, is you can click the plus button. This opens a new structure. And then you have the option to add lattice vectors as well as atoms, and however you like. So even if I do it just by here, as you can see here, this is just an example. You can add, for example, a silicon atom here. This you can do in fractional or Cartesian coordinates, it's up to you. What you can also do is just press this import button to import the geometry. Keep in mind here that all this is just create this for myself as well. Then I will just copy this over. So for example, here, if I copy the geometry.info we've just created into a new file on my local machine, and then I open this folder, I get my geometry file, I can drag this in, and this will load the structure within GIMS. So as you can see here, I now have exactly what I would expect. I have my lattice vectors 5.43, and I have all the coordinates. Again, in our geometry file, we have fractional coordinates. So feel free to click the button and verify that this is indeed the structure. Okay, so that's how you relatively, I hope, simply create bulk structures in general here. Now, for the slabs and the surfaces in general, we have some helper functions. So you see here the surface slab construction button, which you can press, and this opens a dropdown. And now we want the 100 surface, as I mentioned. The number of atomic layers is, of course, up to you. If you're really interested in specific properties, this is something you have to converge for your system. In this case, we'll just use 7 atomic layers to construct the slab. So that's the thickness, essentially, of the slab. And then you can add vacuum. On GIMS, you also have some info fields, for example, that for FHI-aims, if you remember the talk yesterday, we use numeric atom-centered orbitals. So that means the basis functions are really centered on the specific atoms. And we don't use plane waves, essentially, to as basis functions. And that means that in FHI-aims, you easily can use large amounts of vacuum. So if you come from more of a pseudo-potential plane wave code, you might be familiar with the concept of converging the vacuum size. This you don't have to even think of in FHI-aims. You can simply type larger vacuums. So you could do 100, 200 angstrom. All this has no noticeable impact on the calculation speed. So let's here just do 40 angstroms of visualization. If I click here to create slab, then you see the structure builder has indeed created a slab, which you can, of course, look up and see what's happening here. It, of course, in this case, used the conventional coordinates, which are 5.53 for x and y. And then we have in z direction 5.43, including the vacuum size. Right, so let's say the thickness of the slab plus the vacuum, which is 40 angstrom. Now, this cell is not the smallest cell that you need to simulate the 100 surface. You actually can convert this cell into its primitive one by clicking here on standardized cells and just clicking the primitive cell. And then you see you actually reduce the amount of atoms to 7 atoms. Remember, we also specified exactly 7 atomic layers. And this will give you the final structure that we want to study. So from this point on, just to extract your geometry, you can click on the export button. And then you have the option for Cartesian or fractional coordinates. So let's here go for fractional coordinates. And then I will also go back to the tutorial itself. So here you, of course, also have the steps again in pictures. So I hope it's easy enough to follow for you all. And this is the geometry file that we have just created. Let me open my file on my machine just so you can verify that this is indeed the same. So as you can see, as expected, we get the same structure from GIMS as well as the one I have here for reference. So what we do now, and by the way, this is the picture. That's what it looks like. You have the slab in the middle, vacuum, total of 40 angstrom of vacuum. So let's work with the surface now. So we run this command to create a new folder and go into that folder to do our calculation. We create a geometry.in file with this content here. So simply copy paste the surface geometry.in. And then we create now the control.in file. Now control.in in this context means these are the computational settings that FHI-aims will use to run the calculation. So here in this example, we're just using a simple ADA functional, no spin polarization. Atomic Zohr scala is the relativistic approximation. a 17 by 17 by 1K grid. So 17 by 17 is more or less converged for this specific system. And we use the 1K point in the direction of the vacuum. So that's actually important. If you need more than one K point in vacuum direction, that really means you don't have enough vacuum in your cell. Because the interaction between, as I said, neighboring images in Z direction should be minimal. And that also means you only need one K point to sample the slab in that direction. In FHI-aims, you actually have safeguards. So maybe you're copying over your control file for a previous calculation and you forgot to change the K grid for the vacuum direction. The code will actually stop and let you know that we think here something is wrong. And then the last part is a simple relaxed geometry. So this will relax the internal atomic positions of the slab. So let's save this file. And now what is missing are still the species defaults. Right? So in FHI-aims, you need to add the specific basis functions, specifications that you want to use for your calculation. The way we do it here is by using CLIMS. So CLIMS has this prepare run comment to do. So you can just run. This will attach the light species defaults for this geometry. So you can check the control.in file. And now you see, indeed, we have the light defaults for the silicon. The last step that is remaining, simply copy in the job submission script on this cluster and submit it with sbatch. And in case you're wondering, SQ is the comment to see what calculations are running, and then you should see a username also to verify that the calculation is indeed running on the cluster. So let's wait a bit for this calculation to finish. I see here user 63, he also changed the name of the run script, so I'm guessing he's familiar with Slurm a bit. Let's just wait. This will not take long. Yeah, see, and there are some other users also running now. So when the calculation is finished, which is the case for me, you will see several new files. So you have the aims.out file. This is the one where we store the output for this specific job submission script. So you can see here, we store the output in aims.out. In principle, in your own work, you can use, of course, different names here. And because we have a geometry relaxation, we get some additional files. So the relaxed geometry is contained in geometry.in.nextstep, as well as we print out the Hessian that was used during the relaxation step. So if we inspect the aims.out file, we can actually see that we have a slab identifier routine. If you search for the string, it's nice to verify if you know you're running a slab system that this worked correctly, because this sets some defaults. So for example, here it correctly identified this is a Z-oriented slab and the vacuum thickness is 40 angstrom. And in addition to just this identification, we also have the K-grid checks. I mentioned this already briefly. What is done is, one, we check for nearly homogeneous K-grid densities in non-vacuum directions. And then we check also in vacuum directions whether we only have one K point. So these are just some sanity checks we're doing because we want to avoid people running expensive calculations where maybe they forgot to put the correct K grid. And yeah, we of course don't want to waste compute time for you. All these checks, by the way, can be turned off with the keyword in case this is what you want to do. So, and always a good check to check whether the calculation is finished. If you see a have a nice day in the next to the last line, then you know your calculation is good. So that's basically it for this part. So we just wanted to have the aims.out file here. So one thing I just wanted to briefly show you, you can of course copy now this folder. So let's do it here. pwd gives me the current working directory. I will copy this one and I will copy it to my local machine. So I can do the rsync -avz. I do the IP address, the path to the folder, in this case, the Silicon 100 in my case. And then I will just copy it to my local machine. That means you get prompted for password. It gets you all the files. And the reason we're doing this here, again, verify that the files are there, is on GIMPs. if you click here on the name, you can go back. You don't have to stay at the structure builder. We actually have an output analyzer. So if you're interested, simply here, upload the file. In my case here, I'm taking it from the solution folder. Of course, you can also just upload exactly the one you have in your machine. It's enough to upload the aims.out. In principle, you can also upload a full folder. That's useful if you outputted additional information like the band structure and whatever in separate files. So, and then we see here nicely our slab. You have some information on how the relaxation goes. So we only need 4 steps to relax. 5 steps to relax here, as you can see. More things on how for example, charge density converges and so on. One thing we also have, so specifically for relaxations, is a short animation. So if you take a look here, you will see some of the slab atoms slightly moving. So you see that the thickness of the slab is varying, but there's not much else happening at the surface. So, for example, here the simple symmetric dimer construction of the silicon does not do much in this 111 cell. But there's actually an interesting thing happening. So some of you might be familiar with this. The silicon 100 is a quite famous example, and it's known to reconstruct to an asymmetric dimer structure, but only if you use at least a 2x1 supercell. So this will not happen if you use the 1x1, which we currently are looking at. But we have a tutorial where this is described in more detail, so you can take a look at this tutorial and actually run the calculations and then see if you can replicate this asymmetric dimer. But in general, what we wanted to show here is briefly, we wanted to introduce GIMS as a tool to analyze structures and outputs for FHI-aims and simple settings you need to run a slab simulation. So as you can see here, you actually don't need to change a lot in your input files to successfully run a slab simulation with FHI-aims. So at this part, let's stop for a second in case some of you are still running calculations or just analyzing. If you have any questions, we're now open, of course, also to answer, before I will continue in a second. Are there any questions from your side? Yeah, there's some user running. It's good. Any other questions to this part? Otherwise, I don't really see anyone asking one, because then I think we can continue. Okay. At least for now, I don't see any. So let's go to the next part. So the next part is the actual heterogeneous catalysis related model. There's a short introduction here to somehow introduce the issue or the problem. So one, it's quite well known that CO2 conversion reactions are particularly important, right? Because whether it's climate change, sustainable chemical processes, but in general, of course, DFT is not the only tool you need to study heterogeneous catalysis. This was also pointed out yesterday, but it's one of the tools that you can use to study these processes at the atomic scale. So what we'll look at is CO2 adsorption on a specific catalyst system, in this case, a cobalt-based catalyst. And we are focusing on the 2 publications that we also talked about yesterday in the webinar. And this is the kind of system that we're looking at. So you have some cobalt nanoparticle adsorbed on an amorphous silica slab. And you're studying here essentially the catalytic behavior with several of different molecules, in this specific case of CO2. The actual study is much more complex than what we are showcasing here. So for example, Ray also tested additive metals and their effect on the catalytic behavior of these cobalt nanoparticles. But as you see later on, we'll focus on the pure amorphous silica slip in this case. Now, one important principle, so if some of you might not be familiar a lot with catalysis work, is the Sabatier principle. So most often optimal catalysts are actually not the ones where the adsorb or the molecule is binding extremely strongly to the catalyst. So in principle, one can say you are aiming for some middle ground between extreme strong adsorption, where you just adsorb the molecule and then it stays at the catalyst, or extremely weak adsorption where it just dissolves right away. So you have to have some kind of balance if you really want to optimize catalytic performance. So that's something to keep in mind, and we'll see this later on also in the tutorial. So that's it for the general introduction. Of course, if you want to read up on more details, I refer to both of the references also here. So let's go to the actual walkthrough part now. And we wanted to start this section a bit different than the last one, because now there's an additional complexity. So in the silicon 100 case, you have silicon atoms in this lab, and there it's fine to use a non-spin polarized approach. Now, if you have something like cobalt, where we know it has magnetic behavior, you have to include spin treatment. And in our case, in FHI-aims, what we use is spin collinear treatment. So we treat spin up and spin down electrons and densities differently. So the full magnetic moment during the calculation is essentially here given by the integral over the difference between the densities of spin up and spin down. And it's really important that specifically for cobalt-based systems, but magnetic materials in general, if you don't treat the spin polarization correctly, you will get both wrong geometries as well as energetics in general. So it's really mandatory that you know what kind of spin polarization and calculations you have to do here. The function that we use throughout the tutorial is the RPBE functional. So that's a slightly different variant of the PBE functional, which is supposed to provide increased accuracy, especially for adsorption energies on transition metal surfaces. And the main reason why we're using it is specifically that it was used in the reference studies that you've seen for this system. So throughout the tutorial, we'll stick with the RPBE functional and also the light basis settings. So you've already seen them in action for the silicon slab. And we just want to note the trends that we show here, and the results are already quite good with light basis settings, but the actual publication results from both of the references are done with tight basis settings. But as you'll see, the difference is not as drastic as you would expect. There's a question in the Q&A from Andrea. Hi, Andrea, thanks for the question. Is spin orbit coupling included? In this example, no. We have so you have the option to include spin orbit coupled as coupling into the calculations. This was not done here. One could test the effect for these kinds of systems. And in general, we also have benchmarks available for how well FHI-aims performs with, for example, spin orbit coupling for band structures of materials. But in this example, no, we're not including spin orbit coupling. So really just going into the simple collinear treatment without spin orbit coupling. I hope that answers the question for this part. Okay. Yes, good. One other note here. If you're studying a lot of complex metal oxides, for example, or it does not only have to be a metal oxide, it can be, in principle, any charged or spin polarized system. And that typically gives you harder to converge calculations. So we also have a separate tutorial, which is mentioned here, which deals with this iron oxide, which is quite a tricky material to get converged and converge to the correct ground state. So if these are systems that are of interest to you and your work, feel free to have a look at the tutorial, which will also teach you some additional strategies on how to handle these systems. Okay, that's just a side note for you. Now, the quantity we want to calculate in the end is the adsorption energy. And the main reason, this was also discussed yesterday in the talk, is that it's really a key descriptor for catalytic activity. So the formula to calculate the adsorption energy is quite straightforward. So you take the total energy of the adsorbate plus the catalyst, and then you subtract the different components. For example, here just the energy of the catalyst as well as the one from the adsorbate. So in total, you would need 3 calculations in this part. For a specific example, we have the CO2 adsorbed structure on this cobalt cluster on the silica slab. And then we subtract here just the energy of the cobalt cluster on the silica slab in one system, as well as here the isolated CO2 molecule. So keep this in mind that we'll have to do all these calculations to get to the actual adsorption energy. And the way we want to start the calculations, we don't want to go directly to the slab system. We want to take some time to first study the cobalt part of this the system, because that's really the tricky one to get these kinds of systems converged. And we'll start relatively simple with the cobalt atom. So go ahead, you can go back a few folder structures and create a new working folder for the silica. So in this case, I'm putting it in cobalt_silica work. And here we'll do the following calculations. So we start just by looking at the simple electronic configuration for cobalt. So some basic chemistry for you. So we have 7 3d electrons as valence electrons, as well as the 4s. The 7d electrons here align in the following way. So you have 2 fully occupied d states, and then you have 3 singly occupied ones. And these are all spin-up electrons according to Hund's rule, meaning you will result in a theoretical magnetic moment of +3 for each cobalt atom. Okay, so keep this in mind, because this is what we'll use to actually initialize the cobalt free atom. Now, in principle, that's important here. Free atom calculations are not straightforward. So you might think, okay, it's just a simple atom, but there's a lot of stuff you have to actually be cautious of when doing free atom calculations. So again, we have a very extensive tutorial on this linked here. If you're interested in free atoms and so on, please have a look there. But to continue, we start creating a cobalt atom folder. And in this cobalt atom folder, we simply create a geometry file. Now, the geometry file contains the cobalt atom and its positions, as well as you can see here the tag of the initial moment. So within FHI-aims, you can give each atom its specific initial spin moment. In this case, we put the spin moment to what we would expect from chemistry. So this is +3. And then we save this file. And as you notice, we don't really have to change anything from the previous calculation where we did periodic systems. So in FHI-aims, that's one of the good things. Because you have numeric atom-centered orbitals, you can treat both isolated atoms, molecules, clusters, as well as periodic systems on the same footing. So you don't actually need periodic boundary conditions to simulate, for example, here, isolated atoms, clusters, and so on. So, and the good thing is you don't have to change anything for the basis sets and so forth. So this is really nice if you want to calculate, for example, total energy differences like we are doing for this adsorption case. And then we create a control file, which again uses the RPB function like before. We now need collinear spin. So that's the main difference to what you've seen already for the silicon case. And we have already initialized the spin. And now we still need the basis functions. To do so, just run the same CLIMS prepare run comment that we had before. This will, and you can verify in your control.in file, add the light species default for cobalt. And again, copy in your submission script, submit, and await. Oops. You can verify, yeah, people are running stuff, great. It actually takes longer to fire up the node than to run the actual calculation, since this is just a simple free atom. But you can see here, this calculation finished. Have a nice day. Took me 114 steps to converge. If you go up a bit, you will find some more information on during the SCF cycle. All this is human readable, as well as here the spin moment in the last iteration. So it's always important for these kinds of systems to verify that you end up in what you expect is the correct spin moment in the converge calculations. You can also see here, this is just taken from the beginning of the aims.out file. This is what it starts with. So it indeed has 5 spin up electrons here in the 3D orbitals, as well as 2 spin down. So that's exactly what you would expect from this picture that we have here. So in general, if you're working on magnetic materials, spin polarized materials, spend some time to really understand what kind of initial structure you expect, whether it's doing literature research and then finding out, or in this case, by chemical intuition. So that's the simple cobalt atom. I hope that worked for you all. But now we go to the next step. So instead of just doing the cobalt atom, of course, what we want to simulate is the cluster. As shown by Ray Miyazaki yesterday, the cobalt cluster they were modeling was supposed to approximate essentially cobalt nanoparticles in the experiments. So the nanoparticles were much bigger size, so they were like 10 nanometers. But that's really too large to do with, let's say, manageable computational resources and DFT. So instead, they focused on smaller clusters. So in this case, a cobalt 20 cluster. Now, what is already known from a lot of literature work on this is that the smaller cobalt clusters actually have reduced magnetic moment per atom compared to the atom. So instead of +3, smaller clusters typically have around +2 per atom. And the bulk value, so that's a cobalt bulk, has a value of around 0.7 per atom. So this is already the information that we need to know, okay, what kind of spin initialization do we need? The other part here is, of course, the cluster model, because you can create this cluster in many different ways. And here we are using the structure that was optimized initially by Farkas and Deleu. So that was what they found to be the stable cobalt 20 cluster structure. And this was re-optimized with FHI-aims in this reference by Ray Miyazaki with RPBE as well as the light species defaults. So exactly the calculations we're doing here. And as I mentioned, this is really the stable configuration. Again, it's not trivial to find a stable cluster configuration. You, of course, have to try out different structures as well as different spin configurations. But let's do the calculation here. Let's copy this. So now, instead of the atom folder, we have a cluster folder. In general, please create new folders for new calculations. If you rerun a simple calculation, you will always overwrite files. So that's just a warning here. And then let's copy in the geometry file. Okay, so we copy in the geometry file. You again have all the atom positions for the cobalt in total 20. And you have initial moments of +2. As I already mentioned, this is what most people find to be a good starting point for smaller cobalt clusters. And you also notice that all the spin moments are pointed in the same direction. So they're all positive, meaning spin up. And that's indeed, so this ferromagnetic configuration is also indeed the one that was found here by Farkas and Deleu to be the stable configuration for the cobalt 20 cluster. And that's the reason we are initializing here in this ferromagnetic configuration. Now, to continue, let's also write our control file. There's not much different to the atom, so it's still collinear RPBE. You notice here we are adding an additional keyword, so that's the output Hirschfeld. And I hope it's quite clear what it does. It outputs the Hirschfeld analysis after the SEF is converged. So with this keyword, you can perform the Hirschfeld analysis at the end of the SEF. The output keyword within FHI-aims invokes a lot of different infrastructure. So when you will work with FHI-aims and do other runs, output always means, okay, the code will output something in addition to what it usually does. In this case, Hirschfeld analysis, this can also be band structure, density of states, different cube files, for example, if you want to write electrostatic potential in a cube file, and all kinds of other things. But in this case, we use it for the Hirschfeld analysis. And then again, add the light species defaults to this file, quickly verify, yes, we have the light ones for cobalt, and then copy in submission script to your folder and submit. See, some other user was quicker than me, but yeah, great. This is submitted. And just wait a bit. This kind of cluster takes, I think, still less than a minute. So that should be no issue to run. Again, notice here this we initialize with the +2 spin moment. That doesn't mean that the structure in general will stay in that spin state. Okay, so for example, I can show you an example here. If the calculation is not finished, but of course you can still look at the current version of the aims.out file. And then if you simply scroll down a bit, you have a lot of information before the run even starts. So it will tell you a lot of information. And then in the first iteration, which is here, you do a lot of different runs. It's a lot of text here, but you don't have to focus on all the intermediate text. I will just let you know in a second what we are looking at in more detail. It does the eigenvalue solution. It prints all the eigenvalues. In this case here, so all this is printed by default, if that's of interest for you. And then in the first iteration, for example, here it prints you the spin moment. So again, this is integrated via the densities for spin up and spin down electrons. So the spin moment actually is only 34. So while we initialize with +2 for each atom, which will result in +40, it doesn't mean that the SDF iterations always stick at this +40. So we don't enforce spin constraints in this in these kinds of calculations here. So let's see quickly. Yes, everything is finished. So let's go back. Have a nice day was there. So everything worked out. You see now here the Hirschfeld output, right? This is done per atom. So it's always projected on the different atoms. And then I will go up a bit to show you the spin moment. Indeed, in this case, the spin moment converged to the +40, which we expect to be the average spin moment for this cobalt cluster in its ground state. So I hope, let's see, that this worked for most of you. And here, again, is just one, for the first atom, the Hirschfeld analysis. You have several outputs here, for example, the charge and the spin moment. So for this specific atom, it's like +2.16, still around 2. And now you have some options to actually analyze this in more detail, if you like. So one is, the info box is quite important, of course. This was also a question yesterday. You don't need to use the Hirschfeld analysis. I'm just using it because it was used in the references. But you could also use something like Bader charge analysis, which is also supported for FHI-aims. Unfortunately, it's not code internally. So you would first have to output the density in a cube file, which is possible, and then read in this density file with an external package. I think we are currently working on a tutorial to describe this process in more detail, but that's possible. Mulliken charge analysis you can, for example, do directly also in FHI-aims. So in general, I would always say it's not clear which method is the best to do these kinds of charge or spin analysis. I would not trust either method, so any of these methods for really absolute values. So if you really want to trust absolute values to absolute certainty, I would not do that for any of these methods. But they are quite good in showing, for example, charge transfer effects, as we'll see later on. Now, one of the nice features in GIMS, which is showcased here, there's also a visualization for the Hirschfeld charges, which I'll show you briefly. So what I do, let's copy this silicon work folder to my local machine. So again, I do this rsync command. I simply switch the folder I want to copy. I still need my password. And this will copy over all my files. Then I go in here to the cluster. This should have now your aims.out file. This file you can upload. So for example, here in the output analyzer, instead of the cobalt, the silicon, I'll do the cobalt cluster. I'll upload this file. Then you have a nice image of your cluster. together with total energies, some visualization for their eigenstates. So that's here what the eigenstates look like, and so on. But you can click here directly on the Hirschfeld projection, and then GIMS reads out the Hirschfeld projections and gives you some nice visualization. Of course, this is not optimal if you're only interested in the absolute values. If you just want to compare, for example, the atoms directly in some analysis script. But I think for visualization, this is already quite nice. You can see, for example, that the most positively charged Hirschfeld or the most positive Hirschfeld charges are for the atoms on the edges, shown here. And we can do similar analysis also later on for the adsorbed system, as you'll see. Okay, so that's another capability here for GIMS. We are still working on improving this kind of interface, so that's still a work in progress, but that's the current state. Instead of just the GIMS output analyzer for visual analysis, you can also use analysis script we have written for you for this tutorial. So this is all done in Python. If you want to use a different programming language, that's of course up to you. We are just doing it here for convenience. So the only thing you have to do essentially is copy this file, which is called Analyze Hirschfeld, and copy it in one folder above in your working folder, Hirschfeld.py. Oops. I will copy and everything, then I will rename. And then you analyze Hirschfeld in the same hierarchy as your cluster and atom folder. And this folder, this function is actually reading out the Hirschfeld information from the aims.out file. In this case, we give as command line argument the folder for the cluster. So cobalt 20 cluster is the name we had here. And then you run it, and it gives you some files and some additional output. So we have 20 atoms that we've read in and analyzed. So in this case, it's all cobalt. Keep in mind that in this script, it's actually hard-coded to the last 20 atoms in the geometry file. The only reason is I just wanted to write a quick script which just takes the cobalt atoms out, because in our geometry files, the cobalt atoms are always the last 20 atoms. And that's what you get essentially here. You get the average charge, the average spin moment, and two files. So if you check your folder, you actually get a JSON and an MD file. If I open this MD file, this will give you a table of the per atom element charge and spin moment in this case, as well as the statistics we have seen here. The same is printed in the tutorial itself. So you can take a look, see if something jumps out to you. But in general, we see what we would expect. So there's no real Hirschfeld charge in total. So they more or less compensate to 10 to the minus 4, which is for a neutral cluster what we would hope would happen. The average spin moment is also really close to 2.0, as you can see here. So it's 1.999. And this is also exactly what we'd expect. We expect an average spin moment of 2.0 in this converged calculation, as we've seen also in the SEF cycle. Okay, so that's the part here on the cluster. I'll ask just a quick question. Is anything here up to here still fine? Is there an issue that you've encountered, or do you want to ask a general question? You can, of course, also simply raise your hand via the Zoom functionality, and we can allow you to talk. So maybe you're interested in actually asking your question, which we would, of course, also appreciate. But that's up to you. Feel free to use any of our support channels to ask. Okay, there's one question. Comment to save files on my local machine. Yes. I will show you again. The comment is exactly this. So you need rsync minus avz. Then you need your username at the IP address. This IP address is exactly the same for all of you. So you can just type in this address. You need colon, and then you need the path. And the dot means it will copy the files to the current working directory you have on your machine. And this will then prompt you for a password. So again, it's rsync minus avz, username at the IP address, colon, the path to the folder that you want to copy, and then dot to copy it into the local folder that you are. So this command you run on your local machine. I have done that, but okay, then what you can do, if you're not sure what happened, in your folder that you currently are, just type in ls to see what kind of files are in your current directory. So this should give you a list of files. And the files you have copied should be there. Unless you have encountered an error message in your rsync comment. But as I mentioned, if you use this one that I've just sent, this will give you also visual confirmation that the files have been copied. So you can also just check what the rsync comment tells you. Okay. If that's if something is still going wrong, you can of course still ask in the Q&A. Andre, for example, can also just write an answer to you if that's necessary. So that's also no problem. So if there are more issues, just let us know. I think otherwise I have not seen additional questions to this part. So I assume that we can continue. So let's go to the next step. And the next step is how do we actually simulate the cobalt nanoparticle on this support system? Now, as I mentioned, this is exactly the system that was studied in the references and was done by Rei Miyazaki. If you are actually interested in the support material, this was also taken from another reference. So that's here reference 6. And it's not straightforward to obtain these kinds of amorphous silica support systems, but it's explained in more detail there. So essentially is you start from some silicon oxide surface, you relax the system, you run molecular dynamic simulations at higher temperatures, and then you cool down the system after another to essentially then arrive at whatever relaxed structure and amorphous structure you get. And what was done then also in here references 1 and 2 was that they took this structure of the amorphous silica and relaxed it with light basis settings in RPBE and then put this cluster on top of it. Now, I just want to point out that finding the stable position for this nanoparticle is not straightforward. So you have many different potential configurations you have to sample. Because of course, in this, especially in amorphous silica, you don't have order at the surface, right? Because it's amorphous. So you have many potential docking sites that are symmetrically inequivalent. So you would have to put the cluster on several of these different sites. To be more exact here, they were looking at CO groups that were exposed at the surface. And then you just absorb the cluster at many different of these sites by removing also always the hydrogen atoms there. And then you let them form here the cobalt-oxygen bonds to bond the slab at the nanoparticle at the surface. And to gauge how strongly these are bound, you calculate the formation energy, which is very similar to the absorption energy we have seen above for the specific system. And then you get essentially a table, in this case, of 32 different configurations that were sampled. And the most stable one is the one that you see here. So this is really the stable configuration that was found for this cobalt nanoparticle on this amorphous silica slab. Okay. The geometry file, of course, is really, really long. So you can take a look at it. You can also copy it directly. What we have done for you is already prepared the output files. And the main reason we did so is that this structure has 417 atoms. So here you're running 417 atoms in a slab, including spin polarization. So the cobalt atoms, again, here have been initialized with a spin moment of +2. And this would take roughly an hour if you use the same scripts that we have here in the tutorial. So instead, we don't want to make you wait around for an hour. So instead, we have prepared these output files, and you can simply run this command in the work folder to copy over the reference. So that's this copper oxide silica reference. You can also take a look in what is contained there. So you just have the aims.out, the control.in, as well as the geometry. The settings, as I mentioned, are essentially the same. So you have the RPBE, you have collinear spin treatment. The initial moment here, that just means all the other atoms are an initial moment 0 except for the cobalt. K-grid, the Hirschfeld output. Once again, this is an additional comment as well as this SE eta limit, which is not important in the context of this tutorial, but was just used while submitting. So this limits the amount of SEF iterations that can be run, and this writes some restart files. And what you have is then after, you then have essentially your aims.out file, which you can look at and analyze, which we'll do in a second as well. Now, one comment I wanted to make is on the dipole correction. So if you're familiar with surface systems in general and maybe have done so in the past, you might know the dipole correction. So what can happen in slab calculations if you have inequivalent top and bottom surfaces, or also polar surfaces, is that there's a dipole in the direction of the vacuum. So in this case, always in the Z direction, which you typically have to correct in most cases to get an accurate electrostatic potential. And this can be done quite easily in FHI-aims, so you can just use dipole correction in your control.in file, as long as the slab is oriented in the Z direction. Now, the reason it was not done here, you could have done so, and it will not change much, but the main reason was this is a neutral amorphous silica slab. So what you don't have is a lot of the crystalline order that you would normally have in like a metal slab or something. And this also means that you induce much less of a dipole moment. And in this case, the adsorption energies are actually, or the changes compared to the adsorption energies are actually quite negligible. But if you're interested in other post-processing work, so for example, the work function, the electrostatic potential, as I mentioned, you would still need to use it if you really want to have accurate results here. So that's also described in more detail in another tutorial, where we calculate the work function as well as a plot of the electrostatic potential average in the X and Y directions. So if you're interested in how to do this with FHI-aims, feel free also to look through that tutorial. Okay, good. Now, this geometry.in file, I've also, in case some of you know, I like to use, in addition to GIMS, also the Vesta GUI, which is a more general GUI. But here you can nicely visualize this silica slab as well as the cobalt nanocluster. Okay, so, and this is really what you get. You see the adsorption sites for several of these cobalt atoms adsorbed on silica, on oxide atoms here. So feel free also to visualize, again, you can do this in GIMS, you can do this in whatever kind of GUI program you prefer. And you can take some time also to look at the structure after the tutorial, or maybe study it in more detail. Now, what I wanted to do is again here. Sorry, this is. Where did I put my script? Silica work. Okay. Yeah, I think I have to copy in again my script, which was this one, which is this Hirschfeld analysis script. Let's just do this here. And then I can run the Hirschfeld analysis again. And this time we want to analyze this kind of system. So what we'll do is specify the folder where this reference result is in. And this will create some new files now. I see one question that was answered. In which cases dipole correction need to be done strictly? I mean, in principle, whenever you can. It usually does not impact performance. In most cases, if you have non-negligible dipoles, it actually can increase also SEF convergence. But more importantly, it corrects the electrostatic potential. Because what usually happens if you have a dipole, you get a non-flat tail in the vacuum of the slab for the electrostatic potential, which you have to compensate. And that's what the dipole correction is doing. But again, as I mentioned, this is explained in some more detail in this part of the tutorial. Or you can also just Google the dipole correction and the many references on it that there already are. So I hope that answers the question here. So to go back to the Hirschfeld analysis, if we open here this file cobalt silica Hirschfeld analysis.md, this contains the results of the Hirschfeld analysis now for the last 20 atoms, as I mentioned, which are all cobalt. And you can already see some slight changes. Now, if you look at the chart here, you actually have quite a few atoms with larger charges than you would expect. So something like 1.7, 1.3, and so on. And actually, if you look at the statistics, so that's just the average over these atoms, you actually get a charge which is 0.06. So that's before in the cluster case, you have 10 to the minus 4. Now you have 0.06. And this indicates charge transfer from the silica slab to the cobalt nanoparticle. The spin moment itself is also slightly changed. So before we had almost exactly 2.0, I think we had 1.999 something for the spin moment. It's slightly increased now to 2.02. So also due to the absorption, due to the electrostatic effects, you don't have the exact spin moment that you would expect for the free cluster model here. And that's what you can see also from the Hirschfeld analysis. And this chart you can look at in more detail. And that's exactly what was done. So the values we have here match exactly the values that are shown here in this picture. Okay, so for example, you can see here there's one atom with 0.17 charge, which is also the maximum value that was observed. And that's the same here as the J site in this plot. So in the J site here is one of the interface atoms of this cobalt cluster, which have a bond to the oxygen. And this really directly indicates charge transfer from the slab to this site. You can visualize the same in Vesta as an example. So if you have here the different atoms, you see that this is the fourth cobalt atom. So if you just go over here, this is the, oops, it's the wrong structure. And I just highlight the fourth atom, which is this one. It's exactly the same as in the picture. It's the one that has here the bond to the oxygen on one of the edges. Okay. And you can go through, of course, all the other atoms and then maybe verify for yourself if this looks like what you would expect. So, and that's the general trend that was seen. So most of the atoms with higher Hirschfeld charges are the ones that have bonds to the silica support. So all the ones here in green. While all the others are typically in a more metallic cobalt state, meaning they have more or less zero Hirschfeld charge. Now, it's interesting or important to distinguish, let's say, metallic sites, so the ones which essentially have no charge transfer, compared to oxidized bonds, so the ones here with positive charge transfer, because they have quite different absorption properties and in turn also catalytic performance. So what we look at is the absorption of the CO2 molecule on the J side. So that's this side here, which is the most oxidized one, right? So that's the one with the value of 0.17 of the Hirschfeld charge. And we'll compare the result to what is seen also in the publication. To calculate the absorption energy, as you've seen in the beginning with the different formulas, we first need to calculate also the reference for the CO2 molecule. And we'll do so by creating a new folder just for the CO2 molecule, create the geometry. So that's simple CO2 molecule with 1.16 angstrom bond length. Copy in your control files again. Here, just RPBE as usual, no spin. It's not needed for CO2, as well as just the relax geometry flag to relax the structure. Add again the light species default. And lastly, copy in the submit script and submit. And this should really be an extremely fast calculation because this is a simple CO2 molecule. So we'll wait shortly and then you can inspect the file. Indeed, it has converged. Have a nice day. It took roughly 3 relaxation steps. You can quickly inspect your geometry.in.next step to verify that this is indeed the same bond length that you obtain here. So with this, we now have already the CO2 reference. Again, just as in the cobalt cluster case, you don't need periodic boundary conditions here. You can simply simulate it as a cluster model. So now we are going to the actual adsorbed system. Similar to the case of the pure cobalt 20 cluster on the silica support, if we add the CO2, it will still not run faster. It will take longer even. So we'll copy in the reference, which is fully converged. So now you have here the CO2 cobalt 20 silica system as well. And this is what the structure looks like. So the cobalt, the CO2 molecule is adsorbed here at the site, at the J site, which is the one that had the highest Hirschfeld charge, the most strongly oxidized cobalt atom in the cluster here. You can also, of course, visualize the structure, for example, in silica to look at it in more detail. One thing you can also check here is compare the bond angle to what you know from the CO2 molecules. For example, here, it's significantly more planar. So here the bond angle is reduced to around 137.6 degrees. Again, to get to this point takes quite a bit of computing time because you add the atom and you still relax the system. So all this takes quite a bit, which is why we skipped the step just for this part of the tutorial. But within here, you should have still all the input and output files. So feel free to take a look also if you're interested. And now the folder structure, as I mentioned, should look like this before we continue. So you have a silica with the adsorbed structure. You have the CO2 molecule as well as the pure cluster on the silica. So the only thing that's missing is now the adsorption energy. You can do this by hand, by the way, if you just extract energies and then subtract them by hand. And that's completely fine and doable. Just out of convenience, we've written a short script that does this for you with some additional output. So just copy in this file and then analyze energies and simply copy over this Python comment. So what it does, it takes in the reference for the catalyst. So in our case, the catalyst is the cobalt 20 supported on silica. The reference molecule that we adsorb is CO2. And then as the last command line argument, you give the adsorbed folder. In principle, you can also give more in case you have more sites that you want to calculate. So what we do, and it gives you some input here, some additional output. But the important point, of course, here is the adsorption energy. So this adsorbed system has an absorption energy of roughly minus 0.36. And that indicates one, it's negative. So that means it's an energetically favorable process. So the CO2 molecule will adsorb at a specific site. And concerning the absolute values, if you compare this to the literature value from reference 1, which we are following, they calculated the energy with tight basis settings instead of just light, and they found a value of minus 0.27. So that's already, I think, quite comparable to what we have here with our lightest basis settings. And so that's the adsorbed adsorption that's shown here on the right side on this oxidized cobalt species. Now, interestingly, if you do the same process again on the metallic side, so that's one of the ones up here, as you remember. So these were the ones where you have almost zero Hirschfeld charge. If you adsorb the CO2 molecule at these sites, you actually get high adsorption energy. That means the molecule is more strongly adsorbed at the metallic cobalt side compared to the oxidized one. And for catalysis, that's actually not as bad, or it's actually not a bad thing, I would say in general, because that just means here or let's say, what's the best way to phrase this? It's been shown in literature that these oxidized cobalt sites are actually better when it comes to creating additional byproducts like methanol and formate. So they actually have higher selectivity while having reduced overall CO2 conversion. So they have lower adsorption energy, or let's say they have a high adsorption energy compared to the metallic cobalt side, meaning less CO2 conversion in general, but that actually helps the catalysis process here. And I think this nicely points back to the Sabatier principle, which I mentioned in the beginning. You don't need to look only at the site with the strongest adsorption energy. You have to have some trade-off between very strong and very low adsorption. So something in the middle is usually quite good when it comes to catalysis. And this trend of the adsorption side was also shown for larger clusters. So in this reference one, they also started a 55 atom cluster on the same silica support, and the trend is the same. So while the absolute values differ then, because slightly different system as well, the trend is the same. And therefore, in their eyes, the conclusion is also valid for larger clusters. And that's the end of this tutorial. You can do many more things for these kinds of systems. So, for example, what was done in the references, which I alluded to in the introduction, you can also introduce additive metal atoms. So, for example, here in the silica slab, you can just introduce impurities near the cobalt nanoparticle and then analyze what kind of change this has on catalytic performance. So, in general, I would refer to both of the references for more details. Especially reference 2 is also quite interesting because they combine experimental results for this catalysis process with the theoretical ones that we've shown here, so atomic features, as well as just DFT calculations to construct a machine learning model which helps predict good catalyst materials for these kinds of systems. So I think that's also a very interesting reference, and it really shows what you can do beyond just doing simple DFT. Okay, so that's this part of the tutorial. And now I'm open for questions, so I hope you enjoyed it up until now and this worked for you. If there are issues, please let us know. We are not finishing right away, but I just wanted to let you know that this is the full tutorial here. Are there questions? In general, now you can ask also any question you want, whether it's FHI-aims or research related in general. So feel free to ask.